So we're going to discuss what we call intermolecular forces of attraction, better known as IMFAs. Intermolecular forces of attraction. And what these actually represent are exactly forces of attraction that occur between a positive charge and a negative charge. Now, you may be thinking, well, this sounds very similar to a bond, but they are not bonds. Bonds are much stronger than intermolecular forces of attraction. Also, bonds are what we call intramolecular, meaning these are within the compound itself. These are forces within the compound itself. So something like sodium and chlorine have a bond between them that is what we call, indeed, sodium chloride. Something like methane gas has indeed carbon-hydrogen bonds. This happens to be a covalent bond. This happens to be an ionic bond. But notice they are happening within the compound themselves. These are very strong interactions, and they are within the compound. Intermolecular forces of attraction are what we call which means between. They are not occurring within the compound, but between different compounds. So for example, what is holding, let's say, sodium chloride to a water molecule? What interaction is holding this in solution? Better yet, water as a molecule is attached or attracted to other water molecules, because in even one little drop of water, we have millions of molecules of water, not just one. So what is holding these millions of water molecules together? These attractions between one compound and another, between one molecule and another, are called the intermolecular forces. The forces of attraction holding just the elements together within a compound or molecule are called intramolecular. So these are bonds, and these are forces of attraction. That's the difference. These are weaker, and these are stronger. So let's take a look at the three types of intermolecular forces of attraction. Alright, so title at the top again. We have actually three different types. We start with the weakest one, which is a London, or what we call a dispersion force. This is the weakest. It occurs mainly in non-polar compounds, and typically you see this in carbon-hydrogen interactions, meaning, again, non-polar interactions. Almost present in almost all compounds. Now, what we also talk about London dispersion forces is that London dispersion forces do have forces of attraction based on charge, but these charges are very weak. In fact, these charges, what we call dipoles, di meaning two, pole is of course pole, that represents a positive and a negative pole. We need these positive and negative poles to attract, because opposites attract. So we of course note a partial charge, which is what we're dealing with here in London forces, a partial charge as a delta plus for a partial positive and a delta minus for a partial negative. We're not talking whole charges here. We're talking partial charges. And on top of being partial charges, they're also temporary or spontaneous. So like flickering lights, they're on and off and on and off and on and off. And when they are on, they attract and they hold these two molecules together. And when they're off, they don't hold them together. So they're not very, let's say, reliable because they're not always there. They're not always on. And so that's why they're not very strong. They're weak intermolecular forces of attraction. They are forces of attraction that hold these compounds or these different molecules together, but they're not strong enough to always be there and to always have a strong presence. So, to recap London forces, they're the weakest IMFA. They're mainly found in nonpolar compounds. They're hallmark found in carbon-hydrogen bonds, and of course they're present in almost all compounds because almost all compounds have some form of a temporary or spontaneous dipole. So last of all, let's show an example of what this would look like. Let's go back to our methane, which is of course a nonpolar compound. Now, what holds this methane to, let's say, the next molecule of methane to the next, to the next, to the next, to make up these millions and billions of methane molecules? First, let's look at the dipoles. The carbon here has a partial negative and the hydrogen has a partial positive. Again, we know that based on the charges and also electronegativities. The more electronegative element, it will have the negative charge. The less electronegative element will have the more positive charge. So, if this methane molecule is adjacent to, say, this methane molecule, and again this is negative and this is partially positive, notice how this partially negative carbon will attract this partially positive hydrogen, as will this partially positive charge attract this partially negative charge. And let's assume maybe there's another carbon somewhere here with hydrogens around it, and this hydrogen will be attracted to that one, and maybe this one here, and you can see what we're forming is almost a network or a labyrinth, so to speak, of a web of these connections. And again, they're happening between dipoles, weak dipoles of different molecules. So that's a London dispersion force. Let's move on to our next IMFA. IMFAs, we talked about the first type, which is a dispersion force. Let's talk about the second kind, which is what we call a dipole-dipole interaction. You may be thinking, how is that different from what we just discussed? Well, these are stronger than London forces, because these are actually permanent dipoles, not temporary. That makes them stronger because they're always on. We're still looking for a positive dipole and a negative dipole that attract one another. But we're not looking so much into nonpolar as we're looking at polar compounds. So there's yet another difference, and a way you can, of course, identify that your compound would form dipole-dipole interactions. So, what does a dipole-dipole interaction look like? Well, let's take a look at something like HCl. If we have HCl, which is, of course, an acid, we know that the hydrogen has the plus charge partially, and chlorine has a partial negative charge, and so on and so forth. And again, this is polar compounds, not ionic, polar, because that's where we still have partial charges. And then, of course, let's say there's another HCl here. This has a partial positive, this has a partial negative. The positive of this and the negative of this attract, as, for example, could, let's say we had an H and a Cl here. That's a partial plus, it's a partial minus, and then this plus maybe attracts this minus. Meanwhile, there's a ClH here, and there's a minus here and a plus here. And then this plus and this minus get together, while this plus and this minus get together. And you can see almost how, again, this labyrinth of connections begins to form. Now, occasionally, we'll have kind of a variation, if you will, of the dipole-dipole, and we call that the ion dipole. And that's when you have a dipole, for example, like HCl has a dipole. But sometimes we have a dipole that is attracted to an ion. Okay, let's say, for example, you have water. And it has a minus charge for the oxygen and a positive charge for the hydrogens. And they are attracted, let's say, to a compound like NaCl, where Na has a full positive charge and chlorine has a full negative charge. At this point, this negative dipole can attract this ion. This is a full-on charge, a full ion. Again, why is it a full ion? Because this is an ionic compound, a metal-non-metal combination. One loses electrons, one gains electrons, and they have a full net positive or negative charge that results from that. The positive coming from the loss of electrons in the sodium, the metal, the negative charge coming from gaining of that electron by the non-metal here, which is chlorine. But in a water molecule, we're not gaining or losing electrons, we're sharing them. We're just not sharing them equally, and that's what's causing this dipole, this partial charge, where the electrons here are indeed being shared. They're just not being shared equally. So the more electronegative element, the one with the negative charge, is pulling these electrons that are being shared slightly closer to itself. But nevertheless, it's still sharing them with hydrogen. That's why they can never have a full charge, but yet a partial charge, because it only has partial ownership of those electrons. Sodium and chlorine have full ownership of their charges, because chlorine has fully acquired that electron and sodium has fully lost it. So getting back to it, you've got an ion right here, which is the sodium, and you've got a dipole here from the oxygen. The negative and positive attract. Here you have a full-on ion of chlorine, the negative, and it attracts this dipole of hydrogen. An ion-dipole interaction. But again, notice how it's happening between two molecules, still making it, therefore, an intermolecular force of attraction. So let's not forget the I in IMFA stands for intermolecular. All right, last of all, let's take a look finally at our third and final intermolecular force of attraction, our third type. And number 3 is a hydrogen bond. And it's not really a bond, even though it has a term bond in it. But as you might have guessed, this is the strongest IMFA. The reason why it's strongest is because it is an interaction between hydrogen, of course, and only 3 other elements. And that is FO. So think of it as phone, as in a phone that rings and you answer it. It's a good mnemonic for fluorine, oxygen, and nitrogen. Only interactions of hydrogen to fluorine, hydrogen to oxygen, and hydrogen to nitrogen are considered to be hydrogen bonds. No other. Now, what is this? This is a very strong and very specific dipole, is how I like to explain it. It is basically a dipole-dipole interaction. A dipole-dipole interaction, just like number 2. The dipole of a positive hydrogen and a negative fluorine. Positive hydrogen and negative oxygen. Positive hydrogen and a negative nitrogen. These are dipole-dipole interactions. They just happen to be very specific for fluorine, oxygen, and nitrogen with hydrogen. That's what brings us up to the specific part. Specific makes them strong. Why so? Because fluorine, oxygen, and nitrogen are very high in electronegativity. They really like to pull on those electrons. And therefore, the sharing of those electrons becomes even less so. And this high difference then, the difference in electronegativities amongst the elements involved in the hydrogen bond, meaning the hydrogen with the fluorine, oxygen, and nitrogen, are what makes this a specific dipole and a strong one. So it's not just a regular dipole-dipole interaction, it is a hydrogen bond type of interaction. Let's take a look at water, which is probably the best example of a hydrogen bond. There's your negative, there's your positive. There's another water, which is positive there, negative there, positive there, say another water here, and you get the point. The positive here attracts the negative here, as this does. This oxygen attracts this hydrogen. This oxygen attracts this hydrogen. Perhaps even you can have another H2O here, and you've got another connection there, and so on. And you can see again these connecting the dots. Everything's now connected. And what keeps these connected is in all of these water molecules are connected to one another. That's why you get that nice, beautiful drop shape when you see a drop of water. And that's why a water has so much force, not only because of its density, but because of its surface tension. It has a very high surface tension. That's why when a tsunami comes, it's not just, yes, the sheer mass and the speed at which the water is rushing, but it's a surface tension. It's why water is used to cut plastic. It is why when you jump into a swimming pool and you don't break the surface of the water just at the right angle, you feel like you have just slapped the water and you've hit almost like a brick wall, a solid. You don't really feel like you have hit a liquid because you're supposed to penetrate the liquid and go right through. Well, water has a very high surface tension, and it's because of this hydrogen bond that it attributes that strength. The next thing we also want to talk about is other types of course, hydrogen bonds. So let's say if you took water here, here's our oxygen and our hydrogen. And let's say you wanted to combine that with, let's say, hydrofluoric acid. You've got a sample of hydrofluoric acid and you want to dilute it. So here's your hydrofluoric acid. Got your positive and your negative dipoles. In order for this HF, basically, this hydrofluoric acid to combine with the oxygen and the hydrogens of water, they must have an attraction, meaning this oxygen that's negative would attract this positive hydrogen. This negative fluorine would attract this neighboring positive hydrogen, and so on and so forth. This is what we call the like dissolves like. They both have hydrogen bonds, so indeed they are both miscible with one another or soluble with one another. And again, just showing you different ones. HF interactions, HO interactions. And if we had a nitrogen here, it could also, for example, form an HN interaction. But this is what we mean by what is miscible with one another, or the like dissolves like. The hydrogen bond and hydrogen bond, the other hydrogen bond compound or containing compounds are soluble with one another because they have similar interactions. A polar compound would do the same. I just showed you in the previous section, if you had HCl here, then the negative of this chlorine and the positive of this hydrogen could also form an interaction. This would be then a dipole-dipole interaction. It's not specific as a hydrogen, but again, polar and polar mix. Hydrogen bond and hydrogen bond just means a specific polar interaction. They mix. But if I took something like, let me make some room here, let's say I took something like methane. Because methane has these positive and negative charges which are very temporary, they're like oil and water. There's no way that this is going to happen. Non-polar doesn't mix with polar. Let's try to get a different color in here. This can combine with this because they're polar interactions. This is a hydrogen bond. It can combine with this HF, which is a hydrogen bond. It can combine with this, which is a hydrogen bond, because these 3 or 4 are all polar interactions. But this non-polar interaction is not going to happen. So, last thing to discuss is the effect of these intermolecular forces of attraction on the relative colligative properties, such as boiling point or freezing point. Let's just do a comparison of boiling points very quickly. And say, all right, if we have London, and this is of course very weak, and we have dipole-dipole, which is strong, and we have hydrogen bonds. which is very strong. What effect do you suppose this would have? Well, because this has a very weak interaction, what this means is that it's really not going to want to stay with the other molecules. There's not a very strong connection holding them together, which means that if you want to boil them, it doesn't take very much to boil. It doesn't take very much to vaporize this particular substance. So we're looking at a relatively small boiling point here. If we were to look at something that has a dipole-dipole, the interactions are stronger, so it's going to take a lot more energy, okay, to break that interaction. That energy comes in the form of heat. How much heat is required to actually get in there and to break this interaction so that these molecules separate and evaporate and rise, right? Because that's what boiling is. These are going to have a higher or elevated boiling point. And of course, the strongest interaction is going to have the highest boiling point elevation. Why is that again? Because it has a strong interaction. To break that hydrogen bond takes a lot of energy. That's why something like water has such a high boiling point, about 100 degrees Celsius. But something like, say, some sort of an alcohol, like isopropyl alcohol, hand sanitizer, if you will. Alcohols have lots of carbons, oxygens, and hydrogens. The oxygen and hydrogen are what give it the dipole, but this carbon kind of weighs it down. It's more of a London force of attraction because it's got tons of carbons and hydrogen interactions as well. So what this does is this part gives it an elevated boiling point, but this lessens it a bit. So it's significantly less of a boiling point than 100 degrees Celsius, because our body temperature is enough to evaporate it, right? You put it on your hands, rub them together, and it's certainly not 100 degrees Celsius. It's much, much less. So that's why we have a lower boiling point there. And then let's pick something over here like, say, gasoline, okay, or some sort of solvent, polish remover. We're looking at a very high concentration of carbons and hydrogens, which mean not a lot of interaction. That's why if you spill gas when you pump gas, or if you spill some solvent when you're thinning out paint, or you put some nail polish remover on your finger, or to maybe wipe off a mark off of something, or you spill some, maybe it evaporates right away. You don't even have to rub anything on it. It certainly would evaporate a lot faster than rubbing alcohol. If you've ever got nail polish remover on your hands or gasoline, you know that it evaporates very quickly. Very low boiling point. Much, much less than 100 degrees Celsius than compared to water. And certainly much less than alcohol that takes at least your body temperature to evaporate. This, in fact, almost feels cool when it touches your skin. So again, that affects these colligative properties in terms of how much these interactions will elevate boiling temperature. And you can compare the same thing to vapor pressures and to freezing points as well.